Okay, let's unpack this collaboration from researchers at UC Santa Barbara, Stanford, and UC Santa Cruz. The paper is titled Reasoning Within the Mind, Dynamic Multimodal Interleaving in Latent Space.
Yeah, and this is a really interesting one, especially for those of you who work with multimodal large language models, the MLLMs, and are always fighting that trade-off between accuracy and speed on these tough reasoning tasks.
So the mission here seems profound, but also, technically very tricky. They want to make MLLMs reason more like humans do.
Right, by dynamically revisiting visual information only when it's actually needed, not just at these fixed, rigid steps that models usually follow.
And to do that, they're introducing something called Dynamic Multimodal Latent Reasoning, or DMLR.
And the really elegant part is that it's a test-time, training-free framework. It works by optimizing a tiny set of internal vectors, they call them latent think tokens, which basically act as the model's iterative mental draft.
A mental draft, I like that. And this draft gets refined through a pretty clever loop. There's a confidence-guided policy gradient optimization to guide the thinking.
And then a dynamic visual injection strategy. Make sure the model only pulls in the most relevant little pieces of the image at any given moment.
And the result? It's a huge win on that classic accuracy versus efficiency curve.
A huge win is right. We're talking significant performance boosts, up to a massive plus 6.81% on really tough benchmarks like MathVista. And it does all this while being way more efficient than methods that rely on explicit reasoning steps.
Okay, so let's jump right into the why. For anyone running these models, we know they can really struggle with complex problems, especially where you need that tight visual and language integration. What is the fundamental breakdown DMLR is trying to solve here?
It really boils down to flexibility, or I should say the lack of it. Current MLLM reasoning usually falls into one of three buckets, and frankly, they all have some major issues.
The first one is probably the most common, right? The textual-only reasoning, the semantic chain of thought.
Exactly. The model generates these intermediate steps using only language before it gives you the final answer.
And that's immediately a problem.
It is. You get this strong linguistic bias because the model is essentially using words to guide its own perception. This means the reasoning isn't visually grounded enough, which leads directly to, well, the problem everyone talks about, hallucination.
So perception and reasoning get split apart.
They get fundamentally separated. The model ends up trusting its own language-based memory more than the actual raw data in the image.
So it's like, if it's solving a geometry problem, the chain of thought might spit out the triangle is isosceles, but because it's not dynamically checking the pixels, that could just be a complete fabrication.
That's a perfect analogy. It's like forcing a student to solve a visual puzzle, but making them close their eyes while they write down the steps.
Okay, so what's the second bucket?
The second is what they call think with images, or the tool-augmented methods.
Right.
And these sound great on paper. The model can, zoom into parts of an image or generate its own visual cues like bounding boxes.
But the implementation is brittle.
Very brittle. You get unstable tool invocation, for one. And for anyone who actually cares about throughput, they just absolutely kill your inference efficiency. You're constantly spinning up external tools, running extra forward passes. It's just a huge overhead.
A very expensive way to think.
Right. And then even the newer methods that try to do reasoning in the latent space, they often need a bunch of extra training, or they rely on these fixed special tokens.
And that rigidity is the real enemy here.
It is. A model just fires its think token, whether it needs visual evidence or not. There's no adaptive allocation of effort.
Which brings us to the core inspiration for DMLR, and this is where it gets really cool. It's based on how you actually solve a visual task.
Exactly. When you're reading a chart or doing a puzzle, you only glance back at the image when your internal thought process hits a snag, a moment of low confidence. Thinking isn't linear.
It's this dynamic back and forth between perception and internal reasoning.
And this wasn't just a hunch. The researchers actually grounded this whole idea in empirical data. They analyzed MLLMs with a metric called the Visual Dependency Score.
And what does that measure?
It basically measures how much the model's output changes if you mess with the visual input.
And the first big takeaway from that was a real wake-up call for the field.
A huge one. Visual dependency is highly uneven. The vast majority of tokens in a reasoning chain, they operate perfectly fine without the image. Only a tiny critical subset of tokens are actually sensitive to the visual features.
So MLLMs are just wasting cycles looking when they don't even need to.
Constantly. And the second, maybe even more crucial discovery was about an internal self-correction mechanism. They introduced this idea of confidence game.
Which measures the change in probability for the correct answer after a reasoning step.
Right, and they found that correct reasoning chains, what they call the T-plus set, showed way higher positive confidence jumps than the incorrect chains.
So simply put, if the model felt a strong surge of confidence during a step, that step was very likely to be correct.
Exactly. And they went further and used GPT-4o to check the quality of the reasoning itself. The faithful chains, the ones that were logically sound, showed much stronger confidence improvement than the spurious ones.
That's a really powerful finding. It means confidence isn't just some random metric. It's an intrinsic, measurable signal of visual faithfulness inside the model.
It's the cognitive trigger they needed, and this is reinforced by their third observation. Hallucinated steps consistently showed lower confidence and weaker relevance to the image. So this signal is what DMLR uses to decide when to step in.
So we know the models are wasting time, and we know they signal their own uncertainty internally. The challenge then is the how. How do you inject this dynamic reasoning without retraining the whole model from scratch?
And that's where the methodology gets really clever, because it's all about test time optimization. And for anyone working in production, this is huge. The base model parameters, they stay frozen.
So you don't need a massive, expensive retraining effort. All the improvement comes from just optimizing a handful of latent vectors.
A tiny set, yeah. The mental draft. Just 4 latent think tokens in most of their experiments.
Okay, but how do you make sure these 4 tokens can actually find better ways of thinking in this, massive latent space?
They use something called stochastic perturbation. You can think of it like gently and controllably shaking the model's internal thought process. They add a little bit of multiplicative Gaussian noise to the current latent state.
Just enough to encourage exploration without making things unstable.
Exactly. And that exploration needs a guide, which is where the confidence signal comes back in as the reward. They use a policy gradient method to guide the updates.
A technique from reinforcement learning, right?
Precisely. They define the reward as the complement of the mean truncated entropy over the top cup most likely tokens. Now that sounds a bit academic.
Yeah, break that down for us.
Just think of entropy as a measure of confusion. So low entropy means the model is very certain about its top predictions. High confidence.
So low entropy equals high reward.
You got it. The policy gradient is just making tiny adjustments to those 4 latent tokens. And it's constantly getting feedback that says, are you more certain now? Yes. Okay, keep going in that direction.
It's optimizing the internal thought process toward maximum decisiveness.
Yes, using a reinforce-based method. It's treating confidence not just as a score you check at the end, but as the active feedback signal that drives the whole refinement process.
But that internal optimization is only one half of the story. If the model is confused, it needs to look at the image again. This is where the dynamic visual injection, or DVI, comes in.
And this is what solves the problem with other methods that just dump the whole image back in, or inject these huge, fixed blocks of visual data. DVI is much more targeted.
Oh, targeted.
At each iteration, the model uses its attention mechanism to pick just a couple of candidate patches from the image. In their experiments, just 2 patches that are the most informative based on its current internal state.
And they create this really smart cognitive loop.
They do. They inject those 2 new candidate patches along with the best patch they found in the previous step. Then they calculate a new reward.
And if the new reward is higher than the previous best reward,
they update their set of best patches. So the model is iteratively refining its thought, checking the absolute minimal visual evidence it needs to boost its confidence, and then updating what it considers the most important part of the image to carry forward. It's the definition of adaptive.
And this isn't just some clever engineering hack. They actually have a theorem to back it up.
They do. Theorem 4.2. It basically proves that DMLR's visual injection increases the mutual information between the latent states and the visual features, which mathematically guarantees that the process enhances the expected confidence.
Wow. So it's a beautifully constructed closed-loop system that's all happening inside the model's head at inference time.
And by bypassing all those slow, expensive text generation steps of explicit chain of thought and avoiding the massive data dumps of other methods, it just strikes this perfect balance.
Flexible enough to grab details when needed, but efficient enough to rely on internal reasoning when it doesn't.
Exactly.
Okay, let's talk about the payoff then. The experimental validation. They didn't just test this on one benchmark, did they? They really put it through its paces.
Not at all. It showed really robust generalization across 7 major multimodal tasks. We're talking tough domains like mathematics reasoning on MathVista and MMath, visual reasoning, multimodal composition.
And the numbers themselves are pretty compelling.
They really are. Even on a general purpose model like Qwen 2.5 VL7B, they saw average gains of plus 1.5% just on the complex math tasks.
But what happens when you apply it to a model that's already built for reasoning, like R11 Vision 7B?
That's where it really shines. It unlocks so much potential. You're seeing average gains of plus 4.5% in math, plus 3.45% in visual reasoning. And that specific MathVista number, that plus 6.81%, that is a major leap forward for these kinds of problems.
But consistency across the board is what's really impressive to me.
It is. Unlike some baselines that might boost reasoning but actually hurt perception, DMLR consistently improved performance across both domains.
Right, let's nail down that efficiency point,
Yeah.
because for anyone running these models at scale, this is where it fundamentally changes the game.
It really does. Explicit methods like multimodal COT, they have to generate these long blocks of text token by token. That is a massive computational bottleneck. It's crippling.
And even other latent methods can be inefficient.
Right, like ISUT. It might inject huge volumes of visual information over and over again, which adds a lot of overhead. DMLR is just smarter, the thinking is all in the latent space, and the visual access is targeted to just 2 or 3 patches. That's how it gets that superior accuracy-efficiency trade-off.
The Ablation study also seems to confirm that this dynamic element is absolutely essential.
Oh, for sure. They showed that if you take out the visual injection completely, perceptual accuracy just drops off a cliff.
But the opposite was also true, right? Giving it too much visual information was also bad.
Yes. Injecting all the visual patches at every single step, even when it wasn't needed, actually introduced instability and hurt performance. The sweet spot was that dynamic approach, where the model learns to focus on a small, stable set of relevant patches.
They also seem to have validated their hyperparameter choices pretty carefully.
They did. They found that 2 to 4 latent think tokens was the most stable. Any more than that, and the optimization process got unstable and performance degraded. It really confirms that the mental draft needs to be concise.
And the amount of noise they added was also a careful balance.
Yep, that sigma of 10%. Just enough perturbation to let the model explore and find better confidence states. Too much noise and everything becomes chaotic. It really shows how this is a subtle, iterative refinement process.
And when you step away from the numbers and look at the qualitative results, the improvement in visual grounding is it's striking.
It really is. You look at the attention heat maps for a standard chain of thought model, and its focus just drifts all over the place. It'll be looking at a completely irrelevant part of the image halfway through its reasoning. It visually loses the plot.
Whereas DMLR stays locked on.
It demonstrates incredibly stable grounding. As the optimization runs, you can see the attention getting sharper and more focused, staying consistently on the task-relevant parts of the image. It's visual proof that the optimization is making the model a better viewer.
And finally, the latent behavior analysis. They used a TSNE visualization to map where these optimized think tokens end up.
And what they found really confirms the whole concept. The optimized tokens form this tight, compact cluster, and that cluster sits right in an intermediate space, bridging the gap between the text embeddings and the image embeddings.
So it successfully created a unified, stable, cross-modal representation, the dedicated mental draft for solving the problem.
Exactly.
So to wrap up this deep dive, DMLR offers this really novel test time framework that successfully mimics a human cognitive process. Checking the visual evidence only when your internal confidence starts to dip.
It uses that internal confidence as the trigger for both refining its own latent thoughts and for dynamically retrieving just the right visual evidence.
And this approach gives you robust, generalizable performance boosts, especially in those really complex, visual-heavy reasoning tasks, all without needing any expensive retraining of the base model.
It really feels like it's solving that perennial problem of accuracy versus efficiency in MLLMs.
I think the biggest breakthrough here is that they managed to decouple the complexity of reasoning from the need to train these massive explicit reasoning chains. They found a more implicit path to better thought.
Which leaves you with a really provocative question to think about. If we can get such robust and generalizable improvements just by optimizing these implicit representations in the latent space at inference time, How fundamentally might this shift our reliance on building these gigantic explicit chain of thought models in the future? We might be moving from the expensive effort of teaching models to reason to simply refining the elegant act of thinking itself.